All right, so in this video, we are going to be talking about the biochemical basis of life. We're going to start talking about different organic compounds. So in this video, we are going to start out with some chemistry basics just to get to your background, get you familiar with some different chemical terms and different chemistry terms before we actually jump into the world of organic chemistry. So the first thing I want you to do is take a couple minutes and jot down everything you notice about this atom. Okay, so you'll probably notice this is a carbon atom. You can see in the middle there is a cluster of dots. Some of them are red, some of them are gray. We've got a ring of blue and then another ring of blue. 2 in the first one, 4 in the second one. So we're going to be looking at these, figuring out what these parts are, and kind of understanding what we're looking at in terms of atoms. So atoms are the smallest unit of an element that retains the chemical and physical properties of that element. So it's the smallest unit. We're going to say that this is the unit of the smallest unit of matter. So matter being all things that take up space. So atoms are going to have very special properties associated with them. We'll talk about elements here on the next slide, but there are a bunch of parts when we look at an atom. So we've got the nucleus in the middle here, kind of like the nucleus for a cell. The nucleus is going to be composed of 2 different particles. We have protons and neutrons. These protons in the blue are positively charged. So you'll see typically they have a little plus sign on them to indicate that they are positive. The way I like to remember it, P for proton, P for positive. Neutrons, on the other hand, the red ones have no charge. They are neutral, so neutrons to neutral. They are more associated with mass of the atom, so they're used for stability and things like that, not so much overall charge. So orbiting the nucleus here, we have this electron cloud, and this is where we find our third particle, the electron. So electrons, you can see over here, are negatively charged. They balance out with the protons. So you see for the amount of protons we have, we should have, there's not enough in here, but we should have the same amount of protons and electrons just because the net charge of this overall should be 0. We should be neutral. We'll talk about when we're not neutral here in a little bit, but those are the 3 particles in an atom that you want to focus on. Now, atoms are grouped by element. So elements are things that cannot be or a substance that cannot be separated through physical or chemical means. So each atom is its own element. And if we separate those particles, we take the protons out, we take the neutrons out, we take the electrons out, it is no longer going to be that element. So these are all going to have different characteristics. You can see this is the periodic table you may be familiar with. We have a couple different groups. We have the metals, the nonmetals, and the semiconductors or the metalloids. So in the periodic table, we're not going to worry about the lanthanides and actinides. Those are for chemistry. But on this table, anything located to the left of this band here, so it's not really marked on here, but we have a band that stretches from boron down here, kind of like that. Anything to the left of this band is called a metal. They have a couple characteristics. They are typically malleable. They can conduct electricity really well. You can see copper here is a really good conductor. Things like iron are good for metalworking and things like that. But they are all going to be solid as well, except for a couple exceptions. You can see mercury here is typically a liquid at room temperature, but otherwise they're typically going to be solid. There is one exception here that should be with the other group. So hydrogen here is combined with this right side of the table to form the non-metals. So the nonmetals are pretty much the opposite of metals. You see that nonmetals are typically either liquid or gas at room temperature, not solid. They're typically really brittle, so they don't flatten really well. They're not malleable. They're also not very good conductors. You can see we're standing in oxygen and nitrogen right now in the air, and it's not conducting electricity. We can't feel any charges around us because they are really poor conductors. This band, however, boron, silicon, germanium, arsenic, antimony, and a couple others down here are called the metalloids or the semiconductors. So these metalloids kind of have properties in between the metals and the nonmetals. They're pretty good conductors. You see silicon over there is good for computers and things like that. So your phones, your computers, your laptops, all that fun stuff has silicon in it. They are somewhat malleable, and they are usually solid but can exist in a couple different forms. But they, like I said, kind of exist in between the metals and the nonmetals. So now one thing to notice with atoms, like I said, the one drawing on the first slide labeling the different parts was actually kind of incorrect. So when we draw an atom, we want to draw it like this with our nucleus in the middle, and we have these different shells. So you'll notice that each shell has a different amount of electrons. You can see the electrons are in blue. Each atom is going to have a different number of total electrons, a total different number of rings, and a different number of electrons in those rings. For example, hydrogen typically has 1 proton to 1 electron, so you see it's only got 1 shell. Carbon, on the other hand, has 6 protons. You can see in the diagram down here, this is the symbol for carbon, so it's got 6 electrons, and its atomic number, something we'll learn about the periodic table, its atomic number is 12, so it has 6 protons, 6 neutrons, and so in order to be neutral, it has 6 electrons. Nitrogen has 7, phosphorus has 15 protons, so 15 electrons, and sulfur has 16, so it has 16. But you can see more rings, more electrons in those rings. And that is because of something called valence electrons. So valence electrons are the electrons on the outermost shell, and they follow the octet rule. So the way we fill up these shells is that all of these shells, except for the first one, want at least 8 electrons to be happy. So you can see the max number of electrons per shell goes 2, 8, 18, 32, and then it typically goes farther out from there. We don't get higher than 32, but in order for an atom to be happy, it needs at least 8 electrons in its outer shell. So, for example, if this shell here had 8, the atom would be considered stable. And these valence electrons are used for bonding. So they're used to combine different atoms to form molecules. And you can see in this one, so this will be a happy atom because it has 8 electrons, but you can see that in order to get all of these, we have to fill up each shell before we get to the next one. So this first row can only have 2. Think helium is atomic number 2, so it has 2 protons, which means it has to have only 2 electrons. So the far right of the group, or the far right on the periodic table, the noble gases, are called the noble gases because they are unreactive, because they have this outer shell filled. So helium has 2, so its outer shell is filled, which is why it doesn't react. The next row needs 8. Typically we see them more in pairs than in singles, or we draw it in pairs rather than singles. And once this second row is filled, we fill the third shell. And then from there we can get bigger as we add more electrons. So take a moment with that knowledge of atoms. I want you to look at these two chemicals. I want you to kind of identify two similarities and two differences between the chemicals. Okay, so this demo is also done in class, so I do actually have these two chemicals. You can see both of them exist in kind of a white powder. And so one similarity is that yes, even though these have different chemical structures, they both exist as a white powder. You can also see that they do have different atoms. This one has sodium and chlorine, while this one has carbon, oxygen, and hydrogen. So different structures. They also have different structures in terms of their overall structure. So this one has two kind of rings and it's much more flat out. This one is very organized in a kind of square shape. And these are both going to be molecules. So molecules are a group of atoms that are bonded together, and they're going to be the smallest unit of a chemical compound that can retain the properties of that chemical compound. So we see these in water. You can see it in something like salt, which this is the chemical structure for table salt. The other one was the chemical structure for sugar. You can also see this is a caffeine molecule, so you can see there's a lot more parts to it. But all of these are going to be groupings of multiple atoms. So you can see there's always going to be two or more atoms. Typically, we see these as different types of atoms as well. You see there's oxygen and hydrogen in water. There's sodium and chlorine in salt. If we see, let's say, oxygen paired together, we consider this to be a diatom or a diatomic molecule. So we have two oxygen stuck together, and typically a lot of gases like to exist as diatoms. So we would consider that to be a compound, but not necessarily a molecule. Molecules are going to have two or more different types of atoms as well. Now, how do we get these? How do we go from from an atom to a molecule? Well, typically this involves bonding. So we can have a couple different types of bonds. We're going to talk about two today, and then we'll talk about two in the next video when we talk about water. Ionic bonds are our first type of bond. And in this type of bond, we have an exchange of electrons. So we can see this in salt. So you see we have sodium, we have chlorine. Sodium has one electron, which it also has another layer inside with two. And chlorine also has that row of two in the middle, but it has 7. And 7's closer to 8 than it is to 0, which makes chlorine really want that last electron. It wants to be full, it wants to be happy, and the best way to get it is to get it from sodium. Sodium has 1 closer to 0 than to 1, so it wants to lose this electron. It wants to give it up. So what happens is the sodium actually will trade its electron over to the chlorine. And what that does is it creates charges. So this chlorine, now it has an extra negative, so it has, let's say, I think it's 14 protons to 15 electrons, meaning it's going to be negative. Sodium is 3, I believe. So it would have 3 protons and 2 electrons, making it more positive. We call these changes in charge ions. So ions are just going to be atoms that have a different charge associated with them. So either a gain or a loss of electrons. We never lose protons in this case. If we lose a proton, we are going to change the element, not change the charge. So if we lose an atom, or if we lose an electron, we become a cation, or a positively charged molecule, because we have more protons than we do electrons. If we gain an electron, we become an anion. You can see these If you've ever looked at batteries, there's a plus and a minus side. So there's a cation or a positive side and a negative side. Same thing with this. We're exchanging electrons. So the sodium in this case is going to be positive, and the chlorine is going to be the anion because it has a negative charge. So the way I like to remember it, cation has a T, looks like a plus sign. Anion has the N, so it is negative. But what if we have a different charge? So ions are usually formed between metals and nonmetals. We're not going to worry about the metalloids in this case because they can, like I said, have the same properties as both, so they're kind of tricky when it comes to balance or figuring out if they're going to form ionic bonds or not. So we're not going to worry about that. Mostly we're going to focus on the metal and the nonmetal for an ionic compound. But what if we don't? Well, if we have two nonmetals, we get a covalent bond. The covalent bond is a sharing of electrons. So rather than one stealing from the other, we have this case where the electron pair is shared between both atoms. So each one, instead of becoming negative, instead they're going to be happy because they're both holding hands. They're both holding that pair of electrons, so they both kind of have it, and that makes them happy enough that they are both content with that pair. So hydrogen needs one more to fill its shell. Oxygen needs two more to fill its shell. So instead we bond with two hydrogens, and that pair now makes both of them happy. So this is going to involve only nonmetals or occasionally metalloids. We won't talk about bonds formed by metals because they don't really bond together. You can't bond together something that wants to give up its electron because there's not really going to be any transfer there. They're both going to want to give them up, and then nobody's going to be happy. So we're not really going to focus on metal to metal bonding. Typically that's in the form of alloys, but that's for a different topic. So covalent bonds, again, nonmetal to nonmetal, and they're going to share their electrons. So what I want you to do is go through these 10 examples. Actually, we're going to omit number 7 and number 3 because they do involve metalloids. But go through these 8 examples and try and identify what type of reaction is forming between these different reactions. Okay, so let's go through these. So hydrogen plus oxygen, we have a nonmetal plus a nonmetal. So we are going to have a covalent bond in this case. Hydrogen to oxygen forms water if it's 2-to-1, so that would be a covalent bond. Sodium to bromine, sodium is a metal, so we have a metal to a nonmetal. That is going to be an ionic bond. Silicon to oxygen, like I said, we're going to skip this one because this is a metalloid. This one does form an ionic bond, however. Fluorine to fluorine, we have a diatom, but when they do share that electron, that is going to be in the form of a covalent bond. Thallium is a metal to oxygen, the nonmetal, that would be ionic. K plus F, if you're looking at your periodic table, K is potassium, F is fluorine, so that is an ionic bond. Arsenic plus oxygen, this is another metalloid, so this is another one that I told you to skip. But arsenic, in this case, is going to form a covalent bond with oxygen. So you can see between number 3 and number 7, we have a nonmetal performing an ionic bond and a metalloid forming an ionic bond and a metalloid forming a covalent bond. Number 8, hydrogen to chlorine, nonmetal to nonmetal, that is a covalent bond. Carbon to bromine, again, nonmetal to nonmetal. And then magnesium to nitrogen is an ionic bond. So the last thing we're going to talk about is carbon, because a lot of what we're going to be talking about in these next few weeks is carbon and the different molecules that it can make. So organic chemistry is specifically the study of carbon-containing compounds. So we're going to focus on organic molecules, and that's not organic as meaning that it has no pesticides. Organic molecules can only be considered organic if they have at least two elements, carbon and hydrogen. It has to have those two molecules or those two atoms in order to be considered organic. For example, H2O, water, is not organic because it doesn't have carbon. Same thing, CO2, carbon dioxide, has carbon but not hydrogen, so it is also inorganic. Now there are a bunch of other molecules or a bunch of other elements that we can include in this. We'll see as we talk about carbohydrates, proteins, lipids, and nucleic acids. You will see a couple other elements: nitrogen, oxygen, phosphorus, and sulfur. So the way I like to remember this, we will go through, and each different organic compound will have its own kind of abbreviation for what elements are in it. But the way I like to remember this is CHNOPS, or schnapps. That's how I pronounce it. So that is my way for remembering what organic compounds or organic elements we can have, but organic compounds have to have the first two. The other four are optional. And this is because carbon is special. So carbon, just a refresher, has 6 protons, 6 neutrons, so it has a atomic mass of 12, which means it has 12 protons, 12 neutrons, which means it also has, or it has 6 protons, 6 neutrons, and 6 electrons, as long as it is neutral. And the special thing about that is that, number one, it only has 6 electrons, which means it's really small. We only have 2 of these shells. The first one's full, so it doesn't do a whole lot in terms of bonding or anything, but we have 4 in this outer shell, which means 2 things. Number one, because it is so small, it likes to make bonds, so it's really reactive, or when it is able to react, it is very willing to do it. And it can form up to 4 bonds, which anything in carbon's group is able to form 4 bonds. But being able to form 4 bonds means you can do a lot of different things with those 4 bonds. For example, you can make rings. So you can see carbohydrates up here are collections of 6 carbon rings. So you can see over here we have these hexagonal rings. Even though there's an oxygen in there, there is a 6th carbon out the top. But we can form 6-sided rings, we can form 5-sided rings. Typically we don't get any smaller than that. There's too much stress involved in those types of bonds. But we can form rings with them. We can form bent and straight chains with them. So you can see over here, this protein is a straight chain. You can also see some chains over in the different nucleic acids and things like that. They can also form single, double, and triple bonds. So depending on how many electrons we share is going to determine whether it's a single, a double, or a triple bond. So for example, if we draw out carbon dioxide, since carbon can form 4 bonds, it makes 4 different pairs. 2 of those pairs are going to go to oxygen. 2 of these pairs are going to go to the other oxygen. So that will be a double bond. If we want to make a triple bond, we have to share 6 electrons, which is still possible. It's a little more unlikely, but you can even see it in a couple molecules down here. So that the nucleic acids can occasionally have, or the proteins can have some, but we can have a variety of different structures that help us to make all sorts of different organic compounds. We're only going to focus on 4 of them. You can see carbohydrates, proteins, nucleic acids, and lipids. But there are a lot more that are available. I mean, different hormones and different chemicals in your body are all made through this special process that carbon can do. So that is where we are going to end this video. Our next video will be on the properties of water. We're going to skip carbon for a minute, talk about water and why it's so important, and then jump back to carbon for the different organic compounds, because one of the different processes that we're going to talk about with organic compounds involves this molecule here. So that's where we're going to end this video. If you have any questions, feel free to email me. I'm happy to answer your questions as they appear. But otherwise, I hope to see you in class.